Hello everyone, Dr. Zia Tahir here. This video tutorial is about 2D heat transfer analysis in ANSYS Workbench, and problem specific problem is steady state heat transfer through a composite wall. That is a description of the problem, and that is a composite wall. So that is inside room and that is outside ambient, like outside. So the first one is plaster wall, then fiberglass insulation in between them, and then the plywood. So the composite wall of a house shown in figure is composed of 2.5 centimeter thick plaster wall. Thermal conductivity of plaster wall is 0.20 watt per meter per Kelvin on the inside. A 9 centimeter thick layer of fiberglass insulation, K equal 0.038 watt per meter per Kelvin, and a 1.25 centimeter plywood layer with thermal conductivity 0.12 watt per meter per degree Celsius on the outside. The inside room temperature is 20 degrees Celsius with convective heat transfer coefficient of 10 watt per meter square per Kelvin. The outside air is at minus 20 degrees Celsius with a convection heat transfer coefficient of 20. So to analyze that, assume height of the wall as 20 centimeter. And what is required? Determine the temperature at inner and outer surfaces and at the interfaces. So the temperature here, like the plaster wall, left side, right side, and then plywood, left and right side, that is required. Determine rate of heat transfer through the wall, and then the rate of heat transfer is also required. This is problem 13.10, chapter 13, heat transfer and mass transport, from the book A First Course in Finite Element Method by Daryl Logan, 6th edition. So this is actually from there, but I have modified it to solve in ANSYS. Here are steps which need to follow to perform this analysis in ANSYS Workbench. So there are some main steps, and then there are some uh, small steps in that. So first is the project, then engineering data, then geometry, then model, then setup, then solution, then solve it to get results. This is the third lecture of heat analysis series in ANSYS Workbench. So you can watch two other lectures. The first one is 2D steady state heat transfer analysis of a plate, and then 3D steady state heat transfer analysis of a slab in that playlist ANSYS Workbench thermal analysis. So the first step in ANSYS Workbench you need to do is a project and need to start steady state thermal. So here when you open ANSYS Workbench, so you will have that one. So there are analysis systems, and in that analysis system you have here steady state thermal, and that is a steady state thermal. So I'm going to save it in my computer somewhere. So that project is saved somewhere in my computer as composite wall. So that is the first step. Next step is in engineering data, need to add materials. And for steady state thermal analysis, only thermal conductivity. This composite wall, there are three materials. So plaster, fiberglass, plywood, and the thermal conductivity of uh, plaster is 0.20, for fiberglass is 0.038, and then for the plywood it is 0.12. So here in the engineering data, double click on engineering data, and then you'll have here, click here to add new material. So the new material here is plaster. So that is a plaster, and drag that thermal conductivity into that, And the units of the thermal conductivity are watts per meter per Kelvin per degree Celsius there. And then its value for plaster is zero point 0.2. So that is the first material, plaster, is being created with the thermal conductivity of zero point 0.2. In the same way, other material like fiberglass need to be created. Fiberglass. So three materials: fiberglass with thermal conductivity 0.038, plaster with thermal conductivity zero point 0.2, and plywood with thermal conductivity 0.12. They are being added here. So I am going to uncheck that structured steel, so that will not appear while selecting those materials. So now that materials are being created. The next one is geometry, and we need to select analysis type 2D. For that one, I'm going to just save it and then close it, and then geometry. And here in the properties, analysis type is 2D. Okay, so then that geometry is 2D. Next step is in the geometry, new design modular geometry. Right click on the geometry and then new design modular. It will take some time to open that. So that is design modular, and in that design model, that three different walls need to be sketched. So the first one is a plaster. Its thickness is 2.5 centimeter and height we are assuming as 20. So first need to set units in centimeter because all that sketch is in centimeter. So that units, they are in centimeter, and I want to draw that in XY plane. And the 2D, I'm just using that 2D plane. And for that one, in the design modeler, you need to start with sketch and preferably hot surface, and then give its dimension, then concept, and then generate that surface. So the hot surface is plaster wall, so I'm going to start with that plaster wall. So in XY plane, now in the sketching, first need to go to setting, grid, then it is 2D and snap and major grid spacing. I am going to keep it as 1 centimeter, and then I'm going to divide that into 4. So like as each, uh, there are steps here, there are 4, so it will help me to draw that properly. Okay, so then I'm going to draw here rectangle, so I can start from here, and then it is like, let me do it. So that is 2.5 is required. So now that is 2.5, and then its dimension height, I'll adjust that one. Then you can go to dimension and display dimension, and then in general, so you can see that it is 2.5, but that dimension is 3, so I'm going to make it as 20. Okay, so that one, the first is plaster is being now done. So I go there, and then that is a sketch one, and then go to concept, surface from sketches. So it's say apply, and then generate. So you can see that the first is being generated. So here I am going to rename it as plaster. Okay, so the next one, I need to create other sketch, and for that, this one, remember here operation in add material, so you leave it as it is. Now the next one, you need to go to sketch, probably colder surface, dimension, concept, generate, and then in operation you need to add frozen. You need to add frozen. So now here, so that you have that plaster body. So now here a new sketch. So that is a sketch 2. So for that sketch 2, I'll go here in sketching a rectangle. So I can preferably start from here and then I'll, so its vertical is the same as the previous one, but its horizontal is 9. So I am going to this one as 9. Okay, so it is 7.5 centimeters, so that is 9. So now that's sketch 2. It is 20 centimeter tall and that is 9 centimeter. It is its width. So again, sketch 2. I need to go to concept, surface from sketches, and now here is important. So sketch 2, apply and operation. So for that one, operation is add frozen. So here add frozen, okay, and then generate it. So now that second is being generated, which I am going to rename that as fiberglass. Okay, so if you forgot that one, so then you can go to here and then you can change that to frozen later. So now the next one, you need to sketch the third wall, which is 1.25 centimeter and height is 20. So for that one, here, click here, set sketch 3, and then in the sketching, rectangle, so you can start from there. Okay, so height is the same as 20, then go to dimension, general, and then its dimension is 2.25 centimeters, so I need it 1.25 centimeter. Okay, so height is same. So sketch, concept, surfaces from sketches, apply, and here add frozen there. Okay, and then generate that. So you will have that surface body. So I'm going to rename that as plywood. So now those three are being created. So I'll go to sketching and then in the setting, I am going to switch off that grid. Okay, so now you can see that there are three surfaces are being created. So the first one, it has dimension as 2.5. The second one is 9 and the third one is 1.25. Here you can see 2.5. Now once it's being done, so then save this design modeler. Once it's saved, so you can close it. Next step is a model, and for that one, here you have model. So double click on that. So it will open a new window. So that is a new window being opened. So the first is in the geometry, in the model, then geometry, then material assignment. So here you have model and there's a question mark on geometry. I'm going to expand that. And for that plaster, the missing is assignment, which is material. And I have that plaster for that. Then fiberglass, assign its material. Then for plywood, assign its material. So now for plaster, the material added. For fiberglass, material added. For plywood, material is being added. Next step in the model, you need to use construction geometry to create a path. Why the path is because temperature at these 4 points are required. So this can be done either using a path or then either by selecting nodes on these. But I'll go for creating path. So why the path is required? Because you need to find out temperature on these surfaces. So for that one, a path can be created or then otherwise the 4 nodes being selected here. So construction geometry, path, definition. So here in the model, here construction geometry, path. So that is a path x well, so that you can see it's there. So I want to start first point from here. So then it will be now. The geometry was created, the unit was centimeter, but now the standard units here you can see they are meter. So I want to continue with these standard units. Okay, so for that one, then its y coordinate will become, because the total height is 20 centimeters, so it will be 1. So that 1 is being moved there. And now we need to move 2 by putting its coordinates. So which is point 0.5, sorry, point 0.1. So its total weight is 0.1275. So here you can see that is a point 0.1. That is the point 0.2 of that path. So I am going to rename that path as path A. The next step is to check connection or apply connection and the contact region bonded. And for that one, because already that frozen is being selected, so here you have connection. So there are two connections, like the contact region 1, and that is the contact region 1 between plaster wall and fiberglass. So here you can see that is red and then blue, the contact is between them, and the definition is bonded here. So whatever I'm using here bonded, so if there are some other conditions between them, so you can use that one. And the scope method I'm using here automatic. And then the contact region 2, that is the contact region 2 between fiberglass and plywood, so that is the red and then the blue. And again here type is bonded. Next step is mesh, and for that one element size is required, and that is simple. I'll click on mesh, and then the default is whatever is default. So I'm going for uh, point. I'm going for 0.05 centimeter. So 0.05 e raised power minus 2, and then generate. With 0.05 centimeter, it's very fine mesh and take uh, a lot of time. So I am now modifying it for 0.25 centimeter. So 0.25 centimeter, okay, and then generate. So that is with 0.25, that is some reasonable mesh. Next step is setup and steady state thermal, and we need to apply boundary conditions. So there are two boundary conditions for this. One on inside, temperature is 20 degrees Celsius, and then convective heat transfer coefficient is 10, and the outside it is temperature minus 20, and then convective heat transfer coefficient minus 20. So for that purpose, need to go to steady state thermal and then convection. And I'm going to rename that convection as inside. So for inside, now it says that select geometry. So that geometry is being selected, applied, it's a 1 edge selected, and then for the inside, it is 20 and 10. So the film coefficient is 10 and the temperature is 20. So that for inside it is being applied. So then here I can insert convection, and I'm renaming it as outside. So for outside, that edge is being selected, applied, it's a 1 edge selected. And for outside, it is 20 and the temperature is minus 20. So now the both boundary conditions, they are being applied. A at inside, it is 20 degrees Celsius, 10 watt per meter square per Kelvin per Celsius, and then minus 20 degrees Celsius temperature, 20 watt per meter square per Kelvin. The next step is solution and thermal temperature and the temperature, overall temperature contour plot, and then thermal temperature and temperature along that path which is just created. So that is required. So for that one, here in the solution, here thermal temperature, so that is the temperature, and then another thermal temperature and this temperature along that path. I am going to rename as a path. Okay, and then here is the geometry selection is path, and then the path name is path A there. So that is done. Next step is total heat flux required, and for that total heat flux, again in the solution, thermal, and that's the total heat flux. So that total heat flux of that hole is required. So then now we have temperature and temperature along that path, and then total heat flux. So these are the three inputs which are required. And now I'll just solve that one. It will take some time to get the results. So now in the results, the temperature is required at that path. So for that one, here I can plot that one along that path. Okay, but by default for that path, those are like 47 samples. So let's say I want that for the total length. So 2.5 plus 9, so total length is 1.12.25. So I just divide that by 0.25, which is the mesh element size. So that is 51. So I want 51 steps. So now here I'll go 50, and then for this path only I'll solve, and then you can see that along that path. So that is the temperature profile. So that is temperature. Overall temperature, the maximum is on inner wall, it is like that is the minimum temperature, and outside that is the maximum. So those are the temperatures, and then along that path, that is the plot of that. So 18.544, and then on the outside it is minus 19.72, and then that is along the whole path with a step size of 0.025. And now the results from the book, it is 18.5 on the inside, and outside it is 19.3. So that is pretty much 18.5 and 19.3 on the outside. And then at the interface which is interface is at 2.5, and the temperature at the interface is 16.7 here, that the total distance is 2.5. So at 2.5, that is 16.73, which is exactly, and then at that interface the distance is 11.5. So at 11.5, here somewhere, that is 11.5, the temperature is minus 17.7. So that is the same one. So the temperature matches whatever the analytical results are. So the next step is total heat flux required, and for that one is a total heat flux, and the total heat flux comes as a constant heat flux, which is 14.557, and the total heat flux for this problem is 14.5. So that also matches with the analytical results or the answers in the book. So this is the whole analysis of composite wall. So you can this way by creating a path, or otherwise by selecting nodes. So here you can select a node at that point, then that point with the first node there, and with control. So you can select the nodes, and then on those nodes, here are the node selection. Okay, well, so that is the node selection. So with that node selection, you can simply get those results. Now the summary to solve that problem in ANSYS workbench. So first you need to start a steady state thermal project. Then you need to add materials. So three materials were added. Then the analysis you need to perform is 2D. Then you need to first sketch the first wall, and then you need to sketch the other wall. So when you're going to sketch it, so when you are going to convert that uh, sketch to surface, you need to keep that operation add frozen. Okay, so for that way you will get two uh, surfaces. So it is preferably start from the hot surface and then colder, and then in the last one colder. Then you need to start model, and in the model, in the geometry, you need to assign material to each wall. Then to find temperature distribution or temperature at the inner and outer surface and the interface, you need to create a path, or otherwise you can use nodes for that purpose. And then you need to check connection. So in that case, I'm using that bonded. Then element size, you need to keep that element some element size. And then you need to apply thermal boundary condition, and the boundary condition is convection. And for that one, click on steady state thermal or the setup. And by going to environment, so convection, and then you need to give that inner and outer, and you need to add film coefficient and temperature value. Then in the solution, temperature, and then temperature along that path, and then total heat flux. Then you need to go for in the results, you need to get temperature along that path, and then total heat flux. I hope that you like this video. You can leave your comments for feedback. Thank you very much for watching.